Welcome everybody to the second class today. So let us start with a review of the stuff that we learned today. So usually on Friday I ask to give you problems and then you solve them on the blackboard. Today you can get extra points too. So first thing we do, we start with this matrix and we calculate few things. First thing I need to calculate is a characteristic polynomial of that matrix. So after you answer, don't go to your desk, but come here to that row, go to the assistant, TA, and tell him your number. He will take the score. Good. Second thing, eigenvalues of the matrix. Adam, you choose. No, last person chooses. It's not on me. Who is next? Thank you. Good. Who? Eigenvector for lambda equal 1. Come on. Easy. Even if you do wrong, nothing happens, but you practice. So when it comes at a midterm, it's easier for you. The easiest way is to write 0, 0 there. Or if you want the vector notation, then you can also write it in the way 0 vector. Oh, this is probably better. Tell him to choose. Who is next? They also write what this thing is. Good. Thank you very much. So far, we learned the following thing about our matrix. We learned that the spectrum of the matrix consists of two eigenvalues, 1 and 5. And then we found that the first eigenpair is 1 and 1 over square root 2, 1 minus 1. And the second eigenpair is 5, 1 over square root 2, 1. So next thing, inverse. Okay, now if you are right, then we should have H inverse equal 1. Do we? Compute. No, just compute. So we have, very good. You already have inverse of H. Thank you. Close the constant. So we already have the two matrices, H equal 1 over 2, 1, 1, 1, minus 1, H and inverse 2, 1, minus 1, 1, 1. Very nice. Now, the next step is to make sure that we didn't make any mistake. We also have the lambda matrix. That is a diagonal matrix with the eigenvalue 1 and 5, 0, 0. So the next thing we should make sure is that who? You choose. Is it? Nice. Good. So indeed, we have a good decomposition. Now, what we do now, checking, is very important because it's very easy to make mistake in this type of calculation. So every time when you get H inverse, it's good to multiply them together to get unity. If you get these three matrices, put them together, check if this is indeed your original one. There are often small sign change will give you a stupid result and then all other calculations are useless. So we just verify that our decomposition is good. Now, I want from the eigendecomposition. Of course, this is correct. No, maybe you don't understand. I want this to be computed like we did in the class. H lambda minus 1, H minus 1. And what you wrote is of course correct.
That's not inverse, right? 1/5 is missing. Why? Why did you put 5 and 1 there? Look there carefully. Can you explain why? Look at that matrix and that now explain. Okay, and so 1/2, right? And now we get it. Okay, thank you. Good. So we have inverse completed. Now, next thing I want that's easy to calculate. Good, thank you, very nice. That is it. Yeah. Last thing I want to cool. Come on, there's no difference. I know taking exponent of the matrix sounds strange, but Nothing very special, right? Wait. Just the ones. So these. The last zero, I don't understand. Do you explain? Zero. Thank you very much. Very nice. So, there was example how to do the practical calculations for a given matrix. So in midterm, you will have problems of that type for a few points and problem for a larger number of points for 3 by 3 or 4 by 4 matrices. Of course, to make it more fun. Not difficult, right? I hope that each of you can do that type of calculation. Now the interesting thing, we started with a matrix that is symmetric. So every matrix we are getting here is a symmetric matrix. That's as expected. Good. So this is everything about the class we had before. Now we come back to linear equations. We already started talking about linear equations in a class before. Today we just complete that discussion. of the previous classes, we are solving a linear problem. And this linear problem looks like that. A, x equal b. When A was a square matrix, x was a vector, and b was another vector. This is one of the possibilities. The same equation could look slightly different. You can consider that the number of equations to be solved is larger. A, x equal b, or the number of equations actually smaller. All these three situations corresponds to the same problem that is written here. In the last class, I was showing you how to solve this problem when determinant of A is different than 0. But we can have many other situations. First, this determinant can be 0. Second, this could be that. Then you cannot take inverse of that because it's not a square matrix. Or it can be that situation. Again, you cannot take inverse. Sometimes we should be able to solve this type of problems instead of that. So this class now we will study, we will see how to solve all types of problems of that type. First, we should understand if this problem has solutions or not. So this problem is called system of linear equations. And these systems of linear equations would be inconsistent or consistent. In this case, there is no solution. In this case, depending if the determinant of A is different than 0, there is a unique solution. And when the determinant of A is 0, infinitely many solutions. So first thing that we should learn is how to recognize if we have a consistent or an inconsistent set of linear equations. And that's what we are going to do in a moment. But before doing that, let me do slightly different problem. No, let's do it according to what is. So when you have a set of linear equations, A, X equal B, this matrix A is called coefficient matrix. Now you can create something what is called M, and it's called augmented matrix. And this M is simply made by taking A and adding to this one more column. So it's easy to do. Good? Good. Now, the next thing to be done is to write what inconsistent and consistent means. Inconsistent simply means that rank M is larger than rank A. While in this case, rank M is equal to rank A. Since I never defined the word rank, now it's time for that. But we already see that the condition is very easy. Simply on that matrix M and on that matrix A, you have to do some operation. After you do the operation called rank, you get a number, and simply you check if these numbers are equal or this number is larger. If this number will be larger, we don't have solution to the problem. When these numbers will be equal, there is a solution. So now there's a question how to compute rank. In fact, rank comes in two versions. Raw rank and column rank. What is raw rank? It is the number of linearly independent rows. In B. And column rank is the number of linearly independent columns in B. Is it? Easy. We did this type of logic in one of the first classes when we had the vectors and we counted how many of these vectors is linearly independent from each other. So, for example, if your matrix is a matrix 2, 1, 3, 5, 6, 4, then raw rank is you take rows. This is a vector 2, 1, vector 3, 5, and a vector 6, 4. These three vectors are spanning a space. So let me do it again. These vectors are spanning a space V rho. Now you take the dimension of this space and you get rho rank of B. I taught you all of this. Maybe you don't remember, but we had it in one of the first classes. So 3 vectors. You would say, but our vectors were standing. These vectors are lying down. No difference. It's exactly the same logic. Now, this is for rows. You can do the similar story for columns. First, you take a column 2, 3, 6, 1, 5, 4, make a vector space out of that, and then you calculate a dimension of the column, and that's the column rank of B. So first thing you see is that in fact to decide if linear equations have or don't have solutions, that it can be quite painful. A lot of calculations to be done. You have to find this row rank or column rank. Fortunately, there is a theorem in linear algebra. We are not going to prove it, but I just write it down. The theorem says the following thing. For a matrix B, row rank equal column rank. Which means that we can do the yellow and we can do the blue and we get exactly the same answer. Which is easier? Of course blue is easier because you're spun at only 2 vectors. Here you have to span 3 vectors. So always choose the smaller problem to be done. Since row rank and column rank is the same, we call both of them simply rank and we don't care if this is column or row. Good. So one of the problems to be decided is if this rank of the matrix M and rank of the matrix A is larger or smaller. Theory is here. It's maybe not complicated, but it's a lot of work. So now, is there any shortcut? And the answer, yes. There is a shortcut. There is an easy way of checking if this is a consistent or a non-consistent way. Let us take, for example, equation. X plus y plus z equal 1. X minus y minus z equal 1. X plus y minus z equal 1. In this case, the A is a matrix 1, 1, 1, 1, minus 1, minus 1, 1, 1, minus 1. M is the matrix 1, 1, 1, 1, minus 1, minus 1, 1, 1, minus 1, 1, 1, 1. Now we should compute the rank of A and rank of M. In principle, that's the strategy to go, but there is easier way. First, in a rank A, find the largest non-vanishing determinant. So, first, let's try one by one. Of course, non-zero. So rank is at least 1. Now we go one size larger. This is -1, -1, -2. So the rank is at least 2, because it doesn't vanish. Now we go to the full rank. And we count, let's see, -1, -1, 1, 1, 1, plus 1, plus 1, plus 1, plus 1, correct? These two cancel, looks like 4, correct? So we found that the largest non-vanishing determinant is actually the full matrix A. So the size is like that. So rank of A is equal to 3. Is the largest non-vanishing determinant. Look, that in principle, that simply means that this vector, and this vector are linearly independent. 3 vectors are linearly independent, which simply means that the column rank of that matrix A is 3. Since column rank and rank are equal, then we get the same result. We could go with the same result by analyzing the rows of that matrix, taking this one, and this one, and we will find the same results. So you can do the determinant, you can do the number of linearly independent columns or rows. It's all the same. Now, for M, one thing that we know is that the maximal rank must be smaller than that. Smaller than 3, smaller than 4, of course 3 is smaller than 3. So M has the largest non-vanishing determinant to be 3 by 3. Where is it? Of course, it's this one. So this extra column doesn't change anything. Still, rank of M is 3. Because we found the determinant 3 by 3 inside. Another way of looking at this is that these 3 vectors are linearly independent. So the column rank there is at least 3. Since the 4th one is linearly dependent on that, that doesn't change the rank. Good. So for our case that I just wrote, I was just guessing a linear problem. We found that the rank A and rank M are the same. So our system is consistent, so it has solutions. Now, how many solutions? Well, determinant of A, we already computed, was 4. It means that determinant is non-zero, so there's a unique solution. How to find this solution? Again, it's very easy. X y. Ah, oh, okay, yeah, I understand. But let's pretend we don't see that. Of course you are right. So x would be equal to something, y would be equal to something, and z would be equal to something. Your friend is saying that 2 of them are 0, because of obvious reasons. But let's pretend these coefficients are very complicated, we don't see what they are. So now, what we say is that this is B, This is dx. This is dy. This is dz. Do they teach you that in high school? Or no? Or you don't know what I'm writing as so far? No? Okay. Let me explain. On that blackboard, I have four things. First one is D. D is simply determinant of the matrix A. Dx is a determinant of the matrix M. And let's write this M. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I need to put minuses. Minus, minus, minus. Is a determinant of a matrix M in which the column corresponding to X has been removed. Column corresponding to X are these coefficients, 1, 1, 1. So the first column. So that column is removed. dy and dz again are the determinants of the matrix M. 1, 1, 1, 1, 1, 1, 1 minus 1, 1, 1, 1 This, where the column corresponding to Y is removed. And this, where the column corresponding to Z is removed. So everything you need to do is to compute 4 determinants. After you have 4 determinants, you can find X, Y, Z by dividing the determinant by itself. Did you learn this before? Yes? High school? High school. Not everybody, but some people learned this before. This type of formulas have name of Cramer's formulas. And they are working, doesn't matter how many dimensions you have. Here we have X, Y, Z, so our determinant is 3 by 3, 3 by 3, 3 by 3. But if that would be X, Y, Z, W, V, then the determinant would be 5 by 5. Ten-minute break. So see you again at 19:32.